Last class, we added and subtracted graphs. Now we're going to do the same thing with equations and look at how those equations work when we do things algebraically. So here in A, f of x is x plus 2 and g of x is the absolute value of x. We want to state the domain and range of both f of x and g of x. So one of the things you can think of is you can think of these graphically. I'm going to do f of x here in blue. That's the graph of f of x. And I'll do g of x in green. We can think about those graphs. So based on that, for f of x, our domain is everything, and the range is also everything. For g of x, the domain is still everything, and the range is that your y values are bigger than or equal to 0. So drawing a quick sketch helped me solve that question. Some language that comes up in part B. And what does it mean to have an explicit equation? An explicit equation is when we can write something in terms of x. Thank you. I'm on mute. I'm now unmuted. So an explicit equation is when we can write things in terms of x. So right now in B, you've got h of x equal to f of x plus g of x. This is not an explicit equation because right now it's in terms of their functions. But it's as simple as taking f of x, which was x plus 2, and adding g of x, which was the absolute value of x. And this would be an explicit equation for h of x, because now it's in terms of x only, it's not also in terms of their functions. Yeah, for those of you who arrived late, I'll change the attendance after. And determining its domain and range is a little bit tricky from what it is right now. Okay? First of all, the domain actually would be pretty easy. Is there any x's that you're not allowed to put in here? No. So looking at this equation, it would be really easy to see that our domain is everything. But our range is difficult to see in this situation. So one thing we can do is we could go back to our graphs and say, well, what would happen if I added my graphs together? So I look at my equations, and I look at my graphs. I almost need to make it so I can see everything. There we go. And for example, can you see, 1, 2, 3. We'll just do a few points and see if we can see a pattern. I'll draw my h of x graph in purple. First of all, I'm going to use the y-intercept of 2 plus 0 and get 2. If I plugged in 1, this will be 3 plus 1, that'll be 4. If I plug in 2, this will be 4 plus 1, that would be 4 plus 2, sorry, that would be 6. Okay? If I plug in -1, this will be 1 plus 1, that'll be 2. If I plug in -2, this will be 0 plus 2, that'll be 2. -3 will be 2. And the graph looks like this. Not at all what we would expect based on what the blue and the green looked like originally. That's kind of a weird looking graph. But after I've graphed it, I can now say, oh, my range is y is bigger than or equal to 2. Let me zoom back to the page width here. And I'm going to introduce you to something called piecewise notation. Because my equation was kind of hard to work with because of that absolute value in there. My purple graph, in the end, do you see that your purple graph is two straight lines kind of glued together? And I could tell you what the equation of this half is, and I could tell you what the equation of that half is. And this is sort of what piecewise equations are talking about. And the most common piecewise notation that comes up first is actually this graph. Would you agree that your absolute value graph is really just two straight lines glued together? So the way that we would write that is we would write it like this. And we use these squiggle brackets because we have more than one thing we're going to write. And your regular, just redraw here. Here's your absolute value graph, right? The graph on the right-hand side is just y equals x. The graph on the left-hand side is just y equals negative x. The green absolute value graph is like those two lines, but we only have a piece of one line and a piece of the other line. Part of the reason why this is called piecewise notation. Do you see that you only have this one when the x values were bigger than or equal to 0? Like when the x values are on the right-hand side, we have y equals x. When the x values are on the left-hand side of the y-axis, we have y equals negative x. So what we do is we break up the domain into two different pieces. The piece when the x values were bigger than or equal to 0, and the piece when the x values were less than or equal to 0. So this is piecewise notation for y equals absolute value of x, which lets me say I could also write h of x in piecewise notation. We have the one piece when x is bigger than or equal to 0, and the other piece when x is less than 0. Logically, whenever x is bigger than or equal to 0, do you need those absolute values there? Like if you have the absolute value of 7, was it important that they were there, or could you have just taken them away? Right? Because the absolute value only really changes something if it's a negative inside, right? If it's a positive number inside absolute values, they're not really necessary. So if I know that x is bigger than or equal to 0, this is just like saying x plus 2 plus x. And if I combine those like terms, I would get 2x plus 2. Look at the purple graph that we made. Can you see the slope of 2? Can you see a y-intercept of 2? Does it make sense that that purple part on the right-hand side is 2x plus 2? And what do you do inside an absolute value if the x values are negative? You make it positive. Algebraically, one way to make a negative number positive is to multiply by a negative 1. Right? If I have negative 3 and I want to make it positive, I multiply it by a negative 1. So this will become x plus 2 plus negative x. Because as long as x is negative, if I make it a negative x, and then if I have x plus 2 plus a negative x, that'll simplify to just be 2. Which if you look at your purple graph, can you see that all the y values were 2 when it was less than 0? So sometimes we write an equation that can't be written altogether by itself in piecewise notation, which would allow you to, like, if you wanted to, you could take part of a parabola and add a line to it and make a whole bunch of weird looking graphs by just taking pieces of different graphs and drawing them.
Yeah.
Yeah.
How did you get the top one, like 2x plus 2?
So if x is bigger than or equal to 0, this equation, the absolute value doesn't matter. Because if it's a positive number already, I don't need those absolute values. And then those are like terms. X plus x would give me 2x.
Okay.
But in the second one, if x is less, if this x is a negative number,
Yeah, I get it.
right? Yeah, that x is a negative number. Well, one way that I can make it positive is put a negative in front of it. And then that x and that x are going to cancel out, just giving me 2. And part 3 says write an explicit equation for p of x, and p of x is equal to f of x times g of x. So again, we could write this, an explicit equation is in terms of x only, f of x was x plus 2, and g of x was the absolute value of x. But this is hard to graph. We could take points and do every point again, but if we could write a piecewise function, we might be able to graph it quicker. Okay, so again, if you wanted to graph p of x, right, because the graph will help us figure out domain and range, because they asked for that again. Well, domain is easy. Is there any x values not allowed? No. So domain is everything. But the range is a little bit complicated here. I could just look at my original blue and green graph and multiply y values and see what I get. But if I write the piecewise notation of this one for p of x, well, it changes. It's different when x is bigger than or equal to 0 or when x is less than 0. When x is bigger than or equal to 0, the absolute values don't matter. And if I write this now, this is x times x plus 2. Or x squared plus 2x. I'm going to leave it in factored form, because I think it's going to help us graph it even quicker. When x is less than 0, the absolute value would be negative. So now this would be negative x times x plus 2. And those are actually quite easy to graph. I'm going to graph this piece in blue and this piece in green, using my skills from our very first unit for graphing. Okay? Do you see they're nicely in factored form? So because they're nicely in factored form, I would know that the x-intercepts for the blue one are at 0 and at -2. I also know that is a positive x squared graph, which means it opens up. So its vertex would be down here. And if I graph that entire parabola, I'm going to start with the dotted line. That entire parabola would look like this. But we don't want to graph the entire parabola. We want to just graph a piece of it. Which piece do we want from this parabola? Only when the x values are bigger than or equal to 0. So I'm going to just fill this side in. That's the only piece of that parabola I'm allowed to use. The green one. It has the same x-intercepts. But it opens down, because it would be a negative x squared graph. So its vertex would be here. And if I graph the whole thing, that parabola would look like that. But I only need the piece when x is less than 0. So I take this piece of that parabola. And my final graph apparently looks like this. Both of those pieces put together. Actually a very dangerous graph because it's really, really sharp point right there. If you touch it, you'd probably cut your finger and it would bleed. So now that I've drawn the graph, now, again, from the equation, you can see the domain was everything, but the range is very hard to tell until you've drawn the graph. And in this case, the range is everything. So circle questions 3, 5, and 10.